You are on live, sir.
Okay. Let me welcome all of you to this Institute's colloquium. So today our speaker is Professor Nilesh B. Mehta. He is a professor in the Department of Electrical Communication Engineering. He received his BTech degree from IIT Madras in 1996 and his master's and PhD degrees from Caltech in 1997 and 2001 respectively. From 2001 to 2007, he worked in USA at the AT&T Research Labs, Broadcom, and Mitsubishi Electric Research Labs. His research focuses on wireless communications. He is a fellow of IEEE, INSA, INAE, and NASI. He is a recipient of IIT Roorkee's Khosla National Award in Engineering, the Shanti Swarup Bhatnagar Award, Hari Om Ashram Prerit Vikram Sarabhai Research Award, the DST Swarna Jayanti Fellowship. He currently serves as a chair of the steering committee of the IEEE Transactions on Wireless Communications and is a member of the IEEE ComSoc Awards Committee. He served on the executive editorial committee of the IEEE Transactions on Wireless Communications during 2014 to 17 and was its chair during 2017 to 18. He served on the board of governors of the IEEE Communication Society from 2012 to 15. So with this brief introduction, now let me welcome Professor Nilesh Mehta to give his colloquium talk.
Thank you very much, Professor Rangarajan. It's a privilege to give this talk. So what I'd like to talk today about is essentially cellular systems as they are today, the many technologies that it takes to make these cellular systems deliver what they promise, and the different problems that arise when you deal with these technologies. I'll also talk about common threads that arise in these problems, at least one of the common threads that arises in these problems. So to set the context right, I'll go 30 years back and ask the question, what is it that makes cellular technology work? What has made it so prevalent despite the challenges it faces? So the key challenge that a cellular system faces is extremely limited spectrum. Spectrum is scarce and it's extremely expensive. And essentially, when cellular systems were first designed, starting from what we say 1G, first generation, to 2G, and now we're in the 5th generation, the idea is that you have very limited spectrum, so you reuse that spectrum at different locations. So for example, in this figure, this is a very typical figure that you would see for cellular systems. Essentially, you'll see a whole bunch of hexagons that are tessellated. And nothing in wireless looks so perfect, but it's a nice way of visualizing and conceptualizing a cellular system. You have essentially the entire bandwidth in this cartoon divided into 3 parts, 3 subchannels, and different subchannels are shown by different colors. In this case, orange, green, and blue. And the point is that there is a frequency that's allocated to this cell. The same frequency is now used in not the adjoining cell, but a cell that's further away. And the basic principle is that the signal decays when it propagates over space. So you exploit the decay in the signal strength, and you ensure that this signal that is coming out from this cell, by the time it reaches a user, is sufficiently weak, and therefore there is interference, but it is not so strong. So essentially, what cellular systems do is, in a way, they embrace interference. Without spatial reuse, you simply can't pull off these systems. It's this thing that lets you, serve several thousand users in a city right now with very limited bandwidth. But the key design principle in at least the conventional cellular systems, 2G means GSM cellular systems, has been that you are very conservative in the way you reuse spectrum. So you make sure the interferers are sufficiently far apart, several kilometers apart if required, and so that the interference you see is very weak. We've come a long way now from these 2G systems. We are now in the era of 5G. This is a buzzword I'm sure many of us have heard about. And there's been a significant evolution in the capabilities and also the promises these systems have to cater to. So if you look at 2G, it was roughly a 1990 era technology. We refer to it often by the acronym GSM. And it was revolutionary in the sense that it actually promised high quality voice and mobility. You could walk around with a phone and still get very good quality voice. It also had very simple data capabilities, revolutionary for those days, such as SMS and MMS. We in fact even use it today. So if you look at the data rates, 2G system promised, it was like less than half a megabit per second, pretty paltry rates. A decade later, these systems evolved, and then came 3G, and the acronym that we use for it is wideband CDMA. And this was the first system that promised or tried to deliver mobile broadband. The data rates was much higher than what 2G was giving. You're looking about 100 odd megabits per second type data rates. And a decade later, again, 4G came, because 3G was a great idea, but commercially not as successful as it was envisioned to be. And then 4G came, and that's really where this has been a very commercial success, a technology that we're seeing in India now. It's getting rapidly deployed in India now. And what it promised was much better mobile broadband, much higher data rates. I'm being a little fast and loose with these numbers, but you can get the idea of how things have improved significantly from one generation to the next. So now we're talking about 500 plus megabit per second type rates, a much better broadband experience. And now we're looking at 2020. So now we are in the era of 5G, or also what's called new radio, NR. And this is a slightly different beast. It's not just much faster, much better mobile broadband, but now they're talking of industry verticals, multiple services, things like, of course, better data rates. So from megabits per second, now they're promising gigabits per second, but they're also talking about other things that we never heard about before, at least if you're a non-communications engineer. Things like latency. Latency refers to the delay it takes from the time you compose a packet, you transmit it, to the time the receiver receives the packet, decodes it, and makes sense of it, broadly speaking. And we're talking of latencies that are much smaller than 1 millisecond, an order of magnitude lower latencies. So essentially a much more fast dynamic system, and also connection densities of the order of 1 million devices per kilometer square. And so you can see there's been a fairly sea change in the way cellular systems have evolved over the last 3 odd decades. And what I'll be focusing today is on 5G. So if you look at 5G a little bit more carefully, what you'll see is that 5G, like I said, promises not just a much faster, much better mobile broadband, but it promises other things too, or it caters to other things. So now when you look at 5G, people talk about new usage scenarios. And also, of course, this comes with the territory. Also, they have many new acronyms, very stylized acronyms. So for example, there are 3 usage scenarios that they talk about. First is enhanced mobile broadband, EMBB, and that's essentially 4G on steroids. You're talking about promising much higher user data rates, much better spectral efficiencies. And by spectral efficiency, I mean essentially something that's very dear to the heart of an operator. Essentially, it says how much data rate can you pump through a cell per unit time, per unit bandwidth, per unit area. So that's really what the operators care about when it comes to making money. So enhanced mobile broadband is definitely a natural evolution of 4G, but it just doesn't end with that. There's much more to it than that. So the second thing 5G talks about is what's called MMTC, massive machine type communications. So the idea is that you should be able to connect a large number, as large as 1 million devices per kilometer square of low power sensors. For example, applications like the Internet of Things, for applications like equipment monitoring, and so on. There's also another third service. This is a little bit of a tongue twister. It's called ultra reliable low latency communications, URLLC. And the idea here is that you make wireless as reliable as wireline. This is something that has not happened until 5G, but they now want to make it as reliable as wireline. So essentially you have much higher reliabilities. They call it 5.9 reliability, and also much lower latencies. Earlier systems were designed for latencies of the order of tens of milliseconds. They are now talking about millisecond level latencies. And the reason for doing this is that if you can pull it off, you open up a whole new set of applications, things like vehicular networks, where the vehicles can talk to each other in real time. automatic control. So it's not just sensing, but now actuation, factory automation, telemedicine, and many other applications. And so you can see now when you look at a beast like 5G, it has many diverse goals. It's not just unidimensional design. You're trying to improve spectral efficiency dramatically. You're trying to cut down latency quite a bit. You're trying to improve reliability quite a bit. And of course, the energy efficiency is now a critical goal for cellular systems. So you're also looking at energy efficient design. So you have many goals. In fact, some of these goals, when you go about designing the systems, are conflicting with each other. And there's a very nice figure. It's called the spider chart that was brought out by the International Telecommunications Union, which is a global body that defines what 5G ultimately is. And this in a very compact manner conveys the various things that 5G tries to do and how it prioritizes them differently. So I'll walk you through this figure. It's quite interesting. So essentially, there are three concentric circles. The outermost circle is high importance. The middle circle is medium importance, and the central circle is, or the innermost circle is least importance or low importance. Also, you have these vertices here. So, and these refer to the different goals. So, for example, one goal could be mobility. So, can I support users who are moving at pedestrian speeds like 3 kilometers per hour, or users on an Indian highway like 120 kilometers per hour, or even bullet trains that are now they're talking about 500 kilometers per hour. So, how much support should I give for mobility? And this is in fact one of the reasons why we all love cellular technology, because it gives you the ability to talk while being mobile. Of course, there are other goals. For example, the spectrum efficiency. That's, like I said, is how much data can you pump per second, per hertz, or per unit bandwidth per kilometer square. And something which we users care about, which is what sort of data rates do we experience individually when we use the systems. Another goal is peak data rate. This is the marketing number that makes you buy a new mobile phone. Besides the camera specifications, you want to see much higher and higher data rates. This is where the gigabits per second number comes about. You also have energy efficiency, like I mentioned. There's latency, and there's also connection density. How many users can you support? So you can see there are many goals. And what you also see is three different color regions. In green is this enhanced mobile broadband that I spoke about. In blue is the massive machine type communications. In orange is ultra reliable low latency communications. So let's look at EMBB for a minute. So what you see now is that EMBB prioritizes a lot the support for good high mobility, high spectral efficiency, high peak data rates, like you expect. You want things to improve all the time, and so on. And of course, energy efficiency. It doesn't care as much as about connection density. You don't want to handle 1 million mobile users per cell or a kilometer square. You do want to handle 1 million sensors. So EMBB doesn't particularly care much about connection density, and it doesn't care as much about latency. On the other hand, if you look at massive machine type communications, this is shown in the blue region here. You can see that it gives very high importance to connection density and some importance to network energy efficiency. The other goals are, well, yes, they'll be good to have, but they're not showstoppers. Similarly, ultra reliable low latency. This is in yellow here. You can see it cares a lot about latency. Well, it's in the name itself. It also cares a lot about mobility. You want to be able to very high reliability with even when the environment is changing. But other things such as peak data rates and all, they're not that critical. Clearly, these are driven by what your applications are. So you can see that there are multiple services being offered by 5G, and these services cater to conflicting and multiple goals. And the way you solve this problem is by prioritizing these goals to different extents in different services. Now you can ask, wonderful, 5G is promising essentially the sun and the moon. How will it get there? What does it take to make 5G happen? So in a nutshell, the answer is that 5G is not a single technology. It's a collection of technologies and a collection of tricks. So I'll walk you through some of them. First, the tricks. So the first and simplest trick is to cheat. Basically, you throw money at the problem. And what that means is just use more bandwidth. So if you're trying to pump water through a pipe, the best way to increase the amount of water you pump is just buy a fatter pipe. And that's essentially what more bandwidth does. That said, there are other things that you have to do also, because, well, bandwidth is expensive. So the first thing you do is shrink your cells. It's a little counterintuitive at first sight, which is that you can show that if you actually shrink your cells, you make your interferers in a way come closer to, you can actually increase the number of users you can support, so long as you also control the power carefully. So shrinking the cell sizes leads to much higher spectral efficiencies, much higher capabilities in terms of how many users you can serve. For example, when 2G was deployed, people used to talk about inter-site distances, which is the distance between two base stations or two cell towers that were of the order of kilometers. Now people talk about inter-site distances that are order of hundreds of meters or even less now. And it's going to shrink further and further as we go into newer technologies. Another thing is multiple antennas. Some of you might have heard this acronym MIMO, multiple input, multiple output. So the idea is that you have multiple antennas at the transmitter, multiple antennas at the receiver. And what this does is enables you to transmit multiple data streams simultaneously in parallel over the same bandwidth. So so essentially you get a data rate boost that depends on how many antennas you throw at the problem and without requiring more bandwidth. So it's definitely a very appealing thing to do. The last thing you do is anytime you transmit, you try to convey many more bits per symbol. So earlier systems were designed to communicate 2 bits per symbol. Now we've reached a stage where we communicate 10 bits per symbol. So you just pump more data bits out anytime you get a chance to do so. So that's what's called high rate modulation schemes. But this is not just it. This is a very standard bag of tricks now. We are very familiar with it. There are many other things that go into making 5G happen. Some of these technologies are still not incorporated in 5G. People are looking at it. 5G is not a standard set in stone. It's a technology that essentially evolves in releases. So release 15 came out, now release 16 is coming out, and release 17 will come out every year and a half or so. There are many technologies that are incorporated in these standards. So for example, I'll just throw buzzwords at you. These are buzzwords. Do bear with me, but I do want to mention them. I'm not going to explain them. Some of them I'll go into them. But these are buzzwords that arise all the time. They talk of massive MIMO. Remember I said multiple antennas at the transmitter, multiple antennas at the receiver. Massive MIMO says tens or even hundreds of antennas at the transmitter and on the receiver. And doing that has its own very special advantages. People talk about NOMA, non-orthogonal multiplexes, where somehow you can serve multiple users simultaneously on the same band, even though they interfere with each other by using very advanced receiver designs. There's something called dynamic time division duplexing. I better not explain it. Relays that can take your signal and pump it out further so that you get better coverage, for example, cooperative relays, cooperative base stations that synchronized at the symbol level, so at essentially a microsecond level synchronization of base stations to improve reliability of communications. There are other technologies like full-duplex, spectrum sharing, device-to-device communications, and so on. So there are a whole bunch of things that 5G uses to achieve its goals. And what I'll do today is focus on a few of these technologies, especially the ones on the right, and walk you through what's different about them, but also what's common about them. And they make for some very interesting case studies. But now after you do all that, you ask the question, okay, tell me now, how does 5G look like? It's a very surprising picture. Remember the picture I showed you a couple of slides back, where I had this tessellation patterns, different colors, and you made sure the same color never touched. The two cells with the same color never touched each other because you wanted to keep the interference far away. Now, if you look at a 4G system or a 5G system, the story is very different. Essentially, what we do now is something called frequency reuse. We just reuse the entire bandwidth over every possible cell. The trick is, and this is why these systems work and they work better, is they use frequency and they use time at a much finer resolution, and they're much more adaptive to variations in them. Variations could be because of variations in the channel, or variations in the interference, or whatever else. And that's really the trick. So you've essentially not thrown away the concept of frequency reuse, but the whole new bag of tricks that we use now to make it happen. And you can imagine when you have a deployment like this, you have now many new sources of interference. And I'll walk you through in the subsequent slides things like inter-cell interference. This is interference between users in the same cell, and inter-cell interference, which is between users in different cells, users of base stations in different cells. So and this is really what makes the problem technologically challenging and therefore also very interesting. So let's I'll give you a preview of what is coming in the next slide. But before that, just to give you an idea of what is happening under the hood, in a 4G or a 5G system. Essentially, under the hood, here's how these systems operate. I've tried to abstract it out in terms of this colorful cartoon. What they do is they take the entire bandwidth, think of it as 10 megahertz or 20 megahertz. They break it into small chunks. Remember, I said fine frequency resolution. So this is the resolution you're seeing here. Chunks of roughly 200 kilohertz. And you assign these different chunks to different users. And each chunk lasts for a duration of that's just 1 millisecond. Okay, so every millisecond, the base station can say, okay, user pink, you're assigned now. Then it can take it away, give it to another user. This is user gray, or it can give multiple of these resource blocks, as they're called, to a green user, and so on. So it's a very dynamic system where the base station is very constantly monitoring all the channels, and as the channels evolve, which is at the time scale of a millisecond or tens of milliseconds in a wireless system, it very dynamically adapts, schedules users on the fly, and at a very fine resolution. So this is also called orthogonal frequency division multiplexing, and this is what 4G used for the first time, and 5G has continued to use with it. On top of that is MIMO. If you remember, I said MIMO lets you transmit multiple streams simultaneously. So when you put in MIMO, what will happen is you essentially have a similar time frequency grid, just superimposed on the older one, and now you can essentially send two of these grids in parallel on the same bandwidth. So you have two streams now, and today's systems are capable of having 8 such streams in parallel. So this is how 4G systems or 5G systems handle many more users over and in a very dynamic way. And in 5G, in fact, now people are talking of sub-millisecond level scheduling. So you can, in principle, transmit to a user, have the user process the information and acknowledge that it's received the information all within a millisecond. So 4G kind of made things at a millisecond level. 5G is going sub-millisecond level in terms of its scheduling. So that's how dynamic and adaptive these systems have become. Okay, so now let me get to what I want to talk about. Having set the context about 5G, where it's come from, and what it aspires to do. What I'll discuss is three of the many different technologies that 5G uses. And these three technologies are full duplex, device-to-device communications, and spectrum sharing. Why these three technologies? The reason is a biased one. This is something we've been working on for several years now, in some case for almost a decade. What I want to convey to you through this talk is essentially why these technologies are exciting. Why is 5G even looking at them? And also, what are the challenges in making them work in practice? Now, if I do my job right, I would be able to bring out to you that yes, there are different technologies. Yes, there are technology-specific challenges, but there's also a very common theme or a common thread that arises when you design a system, a cellular system, for these technologies. And one of the common themes is interference. How you manage interference, how you control interference, is key to making these systems work effectively. And the last thing I want to do is highlight some of the problems we've looked at, very interesting problems. What I'll do is throw questions out in this talk. I will not discuss the solutions because it's just not possible to go into that level of technical depth in a talk such as this. But hopefully I'll at least convey the very interesting questions that arise and why they even arise and why they're challenging in a way to solve. Okay, so let's get started. The first technology is full duplex communications. So here is a cartoon through which I want to convey why full duplex is exciting. What you have today is today means in 5G. 5G has still not accepted full duplex. People are looking at it for incorporation in future releases. And this is what happens today. All the systems that we use today, your cell phone, for example, your base station, for example, are inherently half duplex. Half duplex means the following. A base station can either transmit to a user, so it'll transmit to a receiver, or it can receive from a transmitter. But it cannot do both on the same band at the same time. It's either this or that, not both. Now, one caveat here, if you ever read your cell phone specs, your cell phone will actually claim that it's a full duplex device. So when they say full duplex, what they mean is that, yes, you can transmit and receive at the same time, but what they do is they do it on two different frequency bands that are separated several tens of megahertz away. No cell phone today or no base station today will transmit or receive at the same time on the same band. And this is what full duplex does. It is a technology that lets the base station That's a cell tower, by the way. And this is the term I'm going to use again and again. I'll even abbreviate it to BS going forward in the slides. So if the base station is full duplex capable, it would be able to transmit and receive at the same time on the same band. And it's kind of easy to see why people are excited by full duplex, because essentially you have one resource and now you're using it twice as efficiently. So essentially your spectral efficiency gets doubled. And given how expensive spectrum is, any technology that promises a doubling of spectral efficiency is definitely worth taking a look. Now you can ask, if this is such an exciting technology, if the solution, I mean, it's almost a no-brainer that you should use it. Then why is it that we're talking about full duplex in 5G? Why was full duplex not possible in 2G? Why did 3G use it? Why did 4G use it? Why did we have to wait 30 years for it? So it turns out pulling off full duplex is seriously not trivial. There are some fairly significant technical challenges that arise when you want to support full duplex. And the biggest challenge is what is called self-interference. And I'm going to illustrate with this cartoon. So consider a base station that is talking to a node R. So it's transmitting to node R and receiving from a node called T. So the base station transmits at a power that's of the order of 10 watts. Okay. And so this is the signal that's blasting. And the signal that it receives, the signal that it's designed to receive, is of the order of a nanowatt, 10 power minus 9 watts. Okay, roughly. I could be off by a factor of 10, but it doesn't matter. These calculations still survive. So essentially what you have is a 10 orders of magnitude difference in the signal that you transmit and the signal that you receive. And what happens in practice is, even though you're transmitting your signal to one node, some of your signal will leak into the receiver. How does it leak? For example, your signal can go out, get bounced off a bunch of reflectors like walls and people and chairs and come back into the receiver of the base station. Yes, it will become weaker, but not so weak that it's comparable to nanowatts. So 10 watts when it comes back will be a factor of 1,000, factor of 10,000 times weaker, but it's still a million times stronger than what the base station is receiving. So essentially this red signal will completely drown out the signal that the base station is trying to receive. There is no way the base station can decode this signal because of self-interference. Another reason self-interference happens is that given how much difference there is between the transmit and receive signals, some of the transmit signal can just leak through internally in your circuitry. So from the transmitter to the receiver, within the circuits, the signal will leak and just reach the receiver circuitry and swamp it out. And you can see, therefore, that unless you get this self-interference under control, unless you cancel it out, unless you essentially shut it down, there is no way you can make a full duplex system work. So self-interference cancellation is essential. And the most important and the biggest challenge with self-interference cancellation is the level of self-interference cancellation capability that you need. There's a reason why we measure things in dB scale, decibel scale. So you need to be able to cancel essentially your transmit signal by a factor of 10 power 10. So in dB scale, it's an easier number to visualize, 100 dB as we say. So that's the level of cancellation capability that you need to build into your base station circuit for the base station to be able to support full duplex capability. And this capability took a long time to develop. It was almost a fairy tale until a decade back. But now there are technologies available for pulling this off. Thanks to work done over the last decade by research groups in Rice University, Stanford University, UCSD. A fairly sophisticated bunch of algorithms have been developed. They involve both hardware as well as software. In fact, it's a multi-stage algorithm, a multi-stage architecture that is used to pull off self-interference cancellation. So I'll try to illustrate this just to give you a feel for why this can happen, so that you at least convince it's no longer a fairy tale. So the essentially three techniques that are used to pull off self-interference cancellation. The first is you isolate your transmit and receive antennas. How do you isolate them? Well, you just coat them with isolating materials. That's an easy one. Other thing you can do is place the receive antenna in the null of, so when the transmit antenna transmits, there are nulls, some locations where the transmitted signal is very weak. You place your receive antenna in that null. So that way, in a way, you get isolation. So remember, we are talking about something like 100 dB of isolation. So this essentially physical layer separation or antenna isolation cancellation give you of the order of 20-25 dB, ballpark numbers. Second thing is the transmitter knows the signal it is transmitting. So the next thing you do is, given that I know the signal I'm transmitting as a transmitter, why don't I just take that signal, weaken it up and cancel it from the received signal. So that's called interference cancellation. That's indeed what I keep saying, self-interference cancellation. So the way it's done is you take your signal when it's just before it goes out of the antenna and you subtract it out from the received signal. The problem with RF is nothing is perfect. 1 minus 1 is not 0 in RF. It is probably 10 power minus 3 or 10 power minus 6. And you can easily see even 10 power minus 6 is too large a number for the kind of numbers we're dealing with. So this is called RF, or radio frequency cancellation. And then the last thing you do is you throw signal processing at the problem. You essentially move everything down to bits, convert everything to samples, convert samples to bits. And now again you say, well, okay, I'm going to cancel out the transmitted signal at the bit level. So you essentially reproduce this entire chain of the signal propagating through all these different modules that I've not told you anything about, goes out of the antenna, comes back. All of these blocks you mimic, and you know what you transmitted. So you can essentially mimic what is coming back in here and then cancel it out. So fairly sophisticated digital signal processing algorithms are used. So this gives you a 25 dB, this gives you 35 odd dB, this gives you 30 to 40 dB, and you add the numbers up, you arrive with 100 dB. So the point is, yes, it is non-trivial, it is challenging, but it can be done now. Okay, and this is really what's made full duplex possible. Now I want to put in a caveat. This is not work we've done. I'm not a circuit designer, so I really don't know how to build these modules. But this is the point at which we entered the picture. And the issue is as follows. Even if you manage to cancel self-interference, it turns out it's still difficult to make full duplex work because there are still many other sources of interference that are very new and novel to full duplex. And let me illustrate this with another cartoon. So here's the base station, here's the transmitter, here's the receiver. Now what we've done is till now I've argued to you that I can essentially kill off this self-interference signal. So I don't need to worry about it. Essentially, it's like noise now. We know how to handle noise. But now you have a very unprecedented scenario where you have a transmitter who's transmitting and a base station also who's transmitting. So this receiver, he's trying to receive the signal from the base station, but he's also receiving an interfering signal. I'll call that cross-link interference from the transmitter. So this is a case where now you have intra-cell interference arising. Interference between users within the same cell. That's what I meant by inter-cell interference. And unless you control this interference, it can again essentially swamp out the signal that the receiver is trying to decode. In fact, you can calculate, and many calculations show, unless you calculate unless you control this cross interference well, you're worse off with full duplex than not using full duplex. Half duplex does much better than full duplex if this interference turns out to be strong. Okay. And this is really where system design questions come. And so let me walk you through a couple of system design questions. Here's the first. Here's the goal first. So what you want to do is control this cross interference, this new interference that's arising because of this unique capability full duplex gives you. Cross interference between users that transmit and receive simultaneously. So what are the kind of questions we need to design for? Which users should be paired for simultaneous transmission reception? Intuitively, you want these users to be as far apart as possible, or essentially have a very weak cross interference. Second, what rate should they transmit at? What transmit power should they use? The larger the transmit power, the larger the rate, but also the larger the interference. And the last question, this is perhaps the most important question of them all, is after doing all this, is full duplex really worth it? Is it going to give me the 2x doubling of spectral efficiency that it promises? Now, how do we solve about this problem? So let me just walk you through the thought process involved in designing cellular systems with full duplex. So remember, our goal is now to carefully choose the transmit and receive pairs. So in this cartoon, I show you a base station that's full duplex capable and lots of users in the cell. Think of this as like 50 to 100 users in the cell. Now, there is a challenge, and this is really the critical challenge. In a cellular system, the transmitter sends the signal, the receiver receives the signal. And based on the signal the receiver receives, the receiver can estimate how much interference it is seeing. The transmitter never knows how much interference it's causing. It's only when the transmitter is told that, hey, you're causing too much interference, that the transmitter knows it's causing a lot of interference. Now, you can see, therefore, that to measure interference or to cross-link interference, I keep saying is very important. Only the receiver would know what the cross-link interference is. The transmitter doesn't know. And no other node in the system will know the cross-link interference in this. So this includes the base station. For example, the base station is not even a part of the link. When 2 transmits, 3 receives, And this is the interference 3 seeing the base station has no clue. So here we are designing a system in which the base station is trying to figure out which users should be paired, but it has absolutely no idea of how much these users are interfering with each other. Essentially, the base station is operating blind. And remember, we're talking of systems that are very dynamic, very adaptive. Well, how can you be dynamic? How can you be adaptive when you're operating blind? That's essentially the question. So this is a common question that arises in every cellular system design, and there's a very simple answer to it. The answer is feedback, and feedback is a trick that's used again and again in system design. So the idea is very simple. OK, fine. I don't know what the interference is, but you please measure it and send it back to me. So for example, user 3 would measure the cross-link interference from user 2. It would measure the cross-link interference from user 3, from all the other users in the cell, and then feed it back to the base station. And therefore, the base station knows which users are encountering a lot of interference, which users are not encountering a lot of interference, and then it can schedule the users appropriately. Now, OK, is the problem solved? The problem is not solved, and for the following reason. If you have n users in the cell, the number of pairs you can construct is n choose 2. So the number of cross-link interference measurements that I need to make and feedback is of the order of n square. It's quadratic in the number of users. And this is an absolute no-no in system design. Most cellular system designs, philosophically speaking, are designed to at best feedback the strength of the signal received from the base station, nothing more. So essentially, cellular systems that are designed today are designed to handle an order n feedback. And even then, they huff and they puff. There are pages and pages devoted in a specification. If you open a 4G standard specification or the 5G standard specification, you'll see pages and pages of schemes that are designed to cut this feedback overhead down. Depending on how you crunch your numbers, even now with order n feedback, they try to cut it down by a factor of 100, by a factor of 1000, depending on how you calculate numbers. So if you have something like order n square, there is absolutely no way a system can support this much of feedback overhead. You know, the way you want to think of this problem is feedback is like bureaucracy. The last thing you want is the bureaucracy to take over and eat up all your taxes and not leave anything for, you know, the roads or electricity or water. And this is what would happen if you don't control your feedback overhead. It's necessary, but it can essentially take over your system if you're not careful about it. And this is the problem that we're looking at. So essentially the problem in a nutshell is what you want is efficient, resource efficient feedback schemes that don't impose too much overhead. And of course, you can easily see the less feedback I send, the less information the base station has, the more blind it is in a way. So you need to be smart about the way you design your feedback scheme. Second thing you need to do is be very smart about the algorithms you design at the base station to pair users, to determine their rates, to determine their powers. In fact, at some point in time, you even have to say, do I really want half duplex or do I really want full duplex? Sometimes it's better off going to conventional methods. How would you do this? And how do you build cells? This is the kind of research problem that arises in this case. And the last question, like I always say, after doing all this, is it worthwhile? So can we characterize or analyze, model and analyze the improvement in throughput due to full duplex? That's the important research question that arises. So I'm going to skip the solution for want of time and move to the second problem. So in a nutshell, to give you an idea of the kind of results we obtained, what we saw was that if you actually try to implement full duplex in 5G, you're not going to get the 2x kind of gains full duplex promises. You get gains of the order of 20-25% in the spectral efficiency. Is 25% a lot? Yes, absolutely. But it is not, 100% gains. So full duplex is wonderful, but it's not going to give you the full gains you get, because when you account for all of these effects in system design, you do lose out some of the gains. Very good. So now let me move to a related technology, but a very different motivation. This is called device-to-device communications, or D2D. There's a very nice acronym they have in the standards for this. It's called PROSE, P-R-O-S-E, and it stands for proximity services. And you'll see why this acronym arises, but they also call it PROSE. And here's the idea. This is actually a technology that's standardized. It was standardized in 4G, never really took off. 5G will also account for it. So again, here's the cartoon that motivates this technology. Why are we interested in it? So today, if there's a transmitter that wants to talk to the receiver, think of yourself and you have a colleague sitting next to you in the same room and you want to talk to the colleague. You call the colleague up. You want to send a data packet to the colleague. You want to WhatsApp a message. What will happen is you'll end up talking, you meaning the transmitter will send the packet to the base station. The base station will receive it, process it, and then at its convenience forward it to the receiver. Then essentially the base station retransmits the packet to the receiver. And that's how the receiver receives the packet from the transmitter. So the base station is the intermediary in today's cellular systems. With D2D communications, device-to-device communications, you set up mechanisms such that the receiver would directly receive the transmitter's packet. The base station is no longer the intermediary. All the base station does is helps these transmitter and receiver hook up so that they know they can talk to each other, and it stops there. It's no longer the intermediary. And you can easily see there are many, many advantages to this technology. This is why this technology is exciting. First of all, you make it a one-hop system instead of a two-hop. One-hop means direct transmission from the transmitter to receiver. Two-hop means transmitter to base station to receiver. Two hops. Why is this exciting? First, it cuts down latency. Latency means time it takes for a message to go from the transmitter to receiver. Clearly, it's coming down. Second thing is, remember I said one of the key tenets of cellular system design is reuse. You want to reuse the frequency as much as possible within the cell. And this is what can happen with D2D. This guy can talk to this guy can talk to this guy can talk to this guy. So you have three D2D pairs all having simultaneous conversations. One application for these people envisage is malls, where apparently this can happen. All on the same band, and you're therefore now able to essentially improve the resource utilization of scarce resource utilization. Another thing is oftentimes these devices are close to each other. That's why these are called proximity-based services. And if you're close to each other, you don't need to yell, you don't need to shout so that your neighbor can hear you. You can just whisper and the neighbor can hear it. So you essentially have lower transmit powers, much lesser energy consumption if you can pull off D2D. And it of course leads to a whole new bunch of proximity-based services which people are excited about. So this is why people are interested in D2D. Okay, wonderful. So this is a great technology, but I guess you know what's coming. What are the challenges? The challenge again has to do with interference. Now you have newer sources of interference when you have D2D communication taking place in a cell. So here's the cell, this is the base station, and this is a conventional cellular user who's trying to talk to the base station. And on top of that, you have two device-to-device pairs. This is one pair talking to each other, this is another pair talking to each other. So what interference happens? First, you have interference from the cellular user to the device-to-device pair. So when the cellular user transmits, its signal will leak out and harass the receiver of the D2D pairs. That's the first thing that happens. That's not it. This is kind of like full duplex territory. We know how to handle it. How do you pair D2D users and cellular users? We know how to answer this question. There's yet another source of interference. The device-to-device users themselves can now interfere with each other. Imagine one pair, second pair, they're all talking on the same band. They will all interfere with each other. So you can see now in a cellular system where a base station typically handles tens of or 50 to 100 users and multiple tens of device-to-device pairs, you have a very complicated interference scenario. And you have many, many options about whom to pair, whom not to pair, who should interfere, who should not interfere, who should transmit on what band. And these are the questions that arise that you need to answer to be able to pull off device-to-device communications. Okay, so what does it take to answer these questions? Here are the questions that you want to answer when you design D2D communications. Which users should be D2D pairs? Clearly, you want them to be close to each other, not far away. Otherwise, they'll keep yelling and interfering with everybody else. Who should transmit on which subchannel? Otherwise, the interference will be a mess. What should their transmit powers be? Higher a transmit power, the more interference you cause. And again, the last question is it worthwhile at the end of the day after worrying about all these questions? How much benefit does D2D bring to the table? Okay, so now a very similar theme slide like in full duplex. Here is the problem. Again, a very similar problem to what we saw in full duplex. The base station does not know the link from the cellular user to the device-to-device pair because it's not part of this link. So it has no idea how much a cellular user is interfering, how much interference a cellular user is causing to any of the other device-to-device pairs. It also does not know anything about how much interference a device-to-device pair is causing to any other device-to-device pair. It's operating blind. But here is it now has to figure out, it has to answer these questions while it's operating blind. So you can again say, hey, come on, let's do feedback. And again, I'll counter and say, if you look at the amount of feedback, if you have M users and N subchannels, you can argue that the feedback overhead is quadratic in the number of subchannels, quadratic in the number of users, and linear in the number of subchannels. An incredibly high feedback overhead, something that's simply not sustainable. So again, the same kind of questions arise. What sort of feedback schemes do I design? Can I pull it off with, for example, just one bit of feedback about each link? I'm not going to tell you the interference, how strong the interference is. All I'm going to tell you is the interference high or mild? That's it, just one bit. How useful is that information? Can I design algorithms that can exploit just this information and do well? These are the kind of questions that arise. And once you answer the question, you can then come up with resource allocation maps like this. So this now says the base station is told, okay, device to device pair 1 and 4 would use subchannel 1. The other guys are going to use subchannel 2 or N, whatever. Okay. These are the kind of questions that you would have to be able to answer to solve these problems. Again, I'm going to skip over the solution. The very interesting questions that arise. You need algorithms that are computationally efficient. Many of these problems turn out to be NP hard. So you come up with approximation algorithms. You also need these algorithms to be feedback aware. You have very less feedback available. Little bit, nothing. It's not nothing, but it's a little bit. You also need these algorithms to be. Remember, we are talking of handling more and more users as we progress from one generation to the other. So these algorithms need to be scalable. And this is really what the holy grail is for this problem. Okay, now for my last about 10 odd minutes. So I'll talk about the last technology, that's spectrum sharing. From its name, it looks very different from the other technologies, but hopefully you'll see in a few minutes that there are again common design threads even with this technology. But first, let me tell you what the technology is and why we are again excited about it. This is about a 15-odd-year-old technology. It's not really new, but it's only got acceptance recently. And here's the motivation for the technology. The way the frequency bands are allocated right now is there is a national level regulator. For example, it is WPC in India. I forget what the acronym stands for. There is FCC, Federal Communications Commission in USA, Ofcam in UK, and so on. These guys decide, okay, you are going to use this band, Airtel is going to operate on this band, Jio is going to operate on this band, ISRO is going to operate on this band, DRDO is going to use that band, and so on. So they are very rigid, predefined allocations. And this is a figure, I'm sure you can't read it. Well, nobody can. It's really small. It's very fine-grained information that tells you who gets to use what. And you have to stick to these bands, otherwise you go to jail. The problem with this is twofold. First is it's rigid. So as the demands evolve, it's really hard to adjust this allocation. These things happen at a time scale of decades, nothing faster than that. So there's a shortage of spectrum for new services. That's the first problem. The other problem is all the more shocking. Even though spectrum is scarce, when people went and measured the utilization of the spectrum, what fraction of time is it used, they found that the spectrum was grossly underutilized by as much as 80%, 60%, depending on which system you see. So not only are you not able to adapt to the new services, you're not able to utilize your current allocation, and yet the spectrum is scarce. It's kind of a crime. So the motivation for spectrum sharing is, well, okay, let's not do a rigid allocation. Let's not allocate one spectrum to just one system. Let's make multiple systems share the same spectrum. That's why the name spectrum sharing makes a lot of sense. If there is a shortage of rooms, you double up students in a room. That's essentially all you're doing. And make sure the students are nice to each other. Being nice to each other has many different flavors, or what are called paradigms of spectrum sharing. So the first paradigm people looked at was called the interweave paradigm. So here's the cartoon that shows it. So there is a primary transmitter and a primary receiver. Think of this as your cellular operator or a military radar communication. So he's the incumbent, this is the person who's been assigned the frequency band. Now you take a secondary system, is shown in green, and you say, please coexist with the primary system. Okay, so there's a reason why it's called the secondary. This is the new system. And given that the primary owns the spectrum already, the secondary has a responsibility, which is that it can use the spectrum, but it should make sure that it does not disturb or harass the primary system. It does not interfere with the primary system. So the interweave paradigm mandates the following. The secondary senses the spectrum. It keeps measuring the channels, the wireless channels, and sees whether the primary is on or whether the primary is off. If the primary is on, the secondary does not transmit, it just shuts up. But the moment the primary turns off, the secondary then goes ahead and sends this information. And the secondary is continuously sensing for the primary to turn on, and the moment it senses the primary to turn on, it shuts up. So essentially, you can see you're interweaving the transmissions of the primary and secondary. That's why this name interweave. And essentially, the key technological challenge is spectrum sharing. You need to be able to spectrum sensing. You need to be able to sense the spectrum and figure out is the primary on and off, and you need to do it carefully. If you are wrong, you can really mess up the primary. So it's a very tight spectrum sharing requirement. Now there's a more advanced version of this, and this is the version that we've been researching for several years now, and that is called the underlay paradigm. And the underlay paradigm motivation is slightly different. In the interweave paradigm, the secondary is allowed to transmit only when the primary is off. In the underlay paradigm, the secondary can transmit even when the primary is on. So in a way, you improve the frequency reuse, you improve the spatial reuse in the system. But there is an important caveat. The secondary is allowed to transmit, but it is subject to very tight constraints on the interference it causes to the primary. So essentially the secondary is told, okay, you can use the spectrum, but make sure you do not harass the primary too much. You do not interfere with the primary too much. That's the underlay paradigm. And with these paradigms now, as of now, spectrum sharing is not legal in India. You cannot do spectrum sharing. But there are cases now where the regulatory agencies, for example, USA is spearheading this effort, the regulatory agencies have accepted spectrum sharing. For example, there is something called the CBRS band, Citizens Band Radio Service, which operates at 3.5 gigahertz carrier frequency. The FCC has opened up 150 megahertz of bandwidth. That's a lot of bandwidth, trust me, for essentially spectrum sharing. And the incumbent user here is one of the important incumbent users is the military radar, US Army and Navy radars. So you have to coexist with these radars. Make sure that you do not harass them. The last thing you want to do is trouble the military. But when the radars don't transmit, which they don't most of the time, you can then essentially decide on your own autonomous spectrum access, as it's called, and transmit. And people are excited about CBRS because there are many new business cases that people like. So indoor 4G networks, what are called indoor LTE networks. So for example, inside factory deployments, you can have a private LTE network. This is one application. Internet of Things, rural broadband, and so on and so forth. There are many interesting applications. About 8 or 9 months back, FCC opened up 1.5 gigahertz of bandwidth, a phenomenal amount of bandwidth at 6 gigahertz. And essentially it's unlicensed, and spectrum sharing is one of the modes that's being considered for 1.5 gigahertz. So it has come of age. Even the regulatory agencies have begun to embrace it. So spectrum sharing is definitely going to happen going forward, if not 5G, in 6G. Now you can ask, okay, this is a wonderful technology, but what are the challenges? The challenge is the following, and it's a very difficult challenge. The secondary is now, here's the challenge. The secondary system has been told you can use the spectrum that's been allocated to the primary, but when you transmit, you will cause interference. I'm showing this by the dotted line here. You have to make sure your interference is constrained. There are severe constraints on the interference. What do I mean by constraint? You can, for example, tell the secondary at no point in time can your interference exceed a given threshold. Another way of saying it is, okay, on average, the interference should not exceed a certain threshold. Or you can say alternately, no more than 10% of the time can your interference exceed a certain threshold. So there are many different ways you can specify an interference constraint, but the bottom line is this interference constraint can really impact the operation of the secondary. Yes, it's better than saying do not transmit, but is it really better than saying do not transmit? If I'm not letting, if there's a teacher in the class who tells the students don't talk, then how can the students talk to each other? That's kind of the problem we deal with. So we've allowed secondary systems to exist or to arise, but then we've really tied both their hands and therefore not allowed them to do anything. And that's really fundamentally the constraint. So now you can ask, okay, here's a very difficult problem. How do you get around it? And turns out there are many techniques. And these are some of the techniques we've been looking at. So I'll illustrate this technique with a cartoon. Here is a secondary system, source, destination. And let's say the transmit signal is very weak. For example, it has to pass through a building. So it's got a very weak signal. So the secondary just can't jack up the transmit power to fight the weak signal, because if it jacks up its transmit power, it'll interfere with the primary. So what do? You can essentially take the help of other nodes. So let's say there are many other nodes in the system. I'm calling them relays. And what you do is you can transmit to one relay, which would then forward the message to the destination. So by using relays, you can essentially now get around this weak path, not have to jack up your power, but still get your message to the destination. And this is the idea of cooperative relaying for spectrum sharing. Okay, so what relays do is essentially provide you multiple paths. And if you're smart enough, as the wireless channels change, and this happens at the rate of tens of milliseconds, you can change your path. So for now, you can choose relay 4, and 10 milliseconds later, when the channels are very different, you can use relay 1 or relay 2 and so on. So these are very dynamic systems that are adapting to changes in the wireless system. And using this, you can now get your job done without harassing the primary too much. Now, this is part of a much broader idea, and it's called spatial diversity. This is spatial diversity because these nodes are spread out in space. So using the fact that if this link is bad, maybe there's an alternate link through a different point in space that's better. You can create spatial diversity, not just using relays, using multiple antennas. I said, MIMO is what I've been saying. This is one way to do this. So you have one antenna, you can transmit from this or this. And depending on how the channels are, you can choose to transmit using the blue antenna or the black antenna. And this is one way to do this. Again, there are many interesting questions that arise in these kind of systems. First question is, which antenna should I use? Which relay should I use? So the answer is, well, use the optimal, use the best antenna. What does best mean in many cases? It's not clear. For example, if I use this relay, how effective the relay is a function of this link and the function of this link. Both these links have to be very good. If even one of these links is broken, there's nothing you can do. Second, it's also a function of how much the relay interferes with the primary. If the relay transmits a relay is very close to the primary, it's essentially going to shut the primary down. So then this path gets ruled out. So you can see now it's a function of multiple things: source to relay, relay to destination, relay to primary. And so defining best is often not obvious. And this is one area of research we've been pursuing, and in many cases we've been able to characterize what best means. Second is, oftentimes these relays don't really know anything about any other relay. If I'm relay 3, I know these 2 links. I know nothing about this link. So you can tell the relay, okay, the best relay transmits, but who's going to tell the best relay to transmit? So you need distributed protocols, distributed multiple access algorithms to tell you which is the best relay. And there are very interesting algorithms that are out there which work for that. And the third question is again a classic system design question, which is, what if I screw up? What if my information is wrong? What if my information is inaccurate? What if my selection is wrong? How much does it impact? And this leads to the question, after all this, is opportunistic selection, as we call this, worthwhile? So again, I'm going to skip the answers to this. They're very interesting answers, and jump to the summary. I have a minute left. So in a nutshell, what I wanted to say is, cellular systems are an integral part of our lives today. They've come a long way from 2G, which is still not that old, to 5G today. 5G is still not there in India, but it's going to happen 2 to 3 years from now for sure. These systems are designed to serve many industry verticals. These are not unidimensional systems. And this is only going to increase when you go to the next evolution of 5G 10 years from now. The other central message I wanted to say is 5G is not a single technology. It's a collection of technologies. Several technologies together, when they're incorporated in these standards, make these standards work properly. Now, in my talk, I hopefully showed you that in many of these technologies, you have to worry about controlling interference from one transmitter to the other receiver. And interference therefore plays a crucial role and even drives system design. And this was true in the 2G era when we first came up with cellular systems, and it is still true today in 5G systems, and it will remain true going forward. And another thing is, when you allocate resources, when I say resources, I mean transmit power, sub-channel, rate. This allocation is often done in these systems, in practical systems with very limited information. You're doing them partially blind. And even then, you have to deliver very high, meet very high goals. And this is really where the interesting problems arise from research. And this is one of the things we've been focusing in my group here. So with this, let me conclude. This is my last slide. I must say what all work I've discussed here is thanks to the work put in by the students. They are the trump card in IISc for all of us. And there's a website here, the students maintain it, and it has up-to-date information about all the work we do. As mentioned in the introduction, essentially I work on wireless systems, and we look at their design, modeling of wireless systems, analysis, optimization, you name it. And lastly, it takes money to do research nowadays, and we've had the generous support of several sponsors over years. For example, right now we have projects on related topics that are sponsored by British Telecom, Intel, and Boeing. So with that, let me thank you for your time.
Yeah, thank you, Nilesh, for a very interesting and a very engaging talk. We have a few questions lined up for you. We will take them up in first come, first serve basis. The first question is by Professor T.V. Srinivas. The question is it correct that faster computing has enabled the new OFDM over finer TF grid?
Has enabled the new OFDM over what? Sorry, I missed that part.
Is it correct that the faster computing has enabled the new OFDM over finer TF grid?
Over finer time frequency grid. I would say the following. I have a contrary view. And the contrary view is the following. Computing is really not the bottleneck when it comes to implementing at least the transmit side of an OFDM system. In fact, the reason people used OFDM was that if you looked at a traditional 3G system, the amount of computing it would require to pull off transmission along with MIMO would be far more than OFDM. So in fact, OFDM is designed to make it easy to compute, not harder to compute. Yeah.
Okay, thank you. There is a question by Professor Jayant Haritsa. Doesn't spectrum overlay also require spectrum sensing to know when to constrain interference and when the whole channel can be used because primary is idle?
Yes, absolutely. So in fact, the way the spectrum overlay would work is the secondary system is sensing. If it senses that the primary is off, I mean, it has a jolly good time. It just fires away, transmits without worrying about interference because the primary is off. But it's also constantly sensing for the primary. Once the primary turns on, unlike the interweave paradigm, now the secondary system will scale its transmissions down. Its transmit power will scale down. It will not shut itself down. That's the difference. So the answer is yes. Yeah.
Okay. So I would request the participants to type out their questions in the live event Q&A if you have more questions. So I had one question myself, Nilesh, namely that you work in full duplex, then D2D communications, and also in spectrum sharing. How much of it can eventually get into 5G standards also?
So the answer in a nutshell is nothing will get into 5G. We are hoping that will get into future releases of 5G. That said, I must say it's a long journey before any of these technologies make it into the standard. Some of these technologies never will because some of them are essentially what the base station does. So it's part of the secret that the base station has. So an operator would be very interested, for example, like BT would be interested in using these algorithms to improve its efficiency. But some of the techniques like the feedback scheme design have a direct bearing on the standard. But it takes a lot of effort to get it into the standard. It takes teams of people and teams of companies to do it.
Okay, thank you. There is one more question by Anonymous. Is it possible to exploit interference in some cases to our benefit?
Yes. I'll give you the simplest example of them all. It has to do with what's called wireless power transfer. It's not the most, it's a very interesting example and this is why I mention it. So typically interference is bad because, well, you can't receive your signal, but sometimes you're better off just using that all the interference you're getting, harvest the energy inherent in the interference and use it to power your sensor nodes. So you can't power a big fat mobile using that, but you've got a tiny little sensor node that has to sense a measurement, every few hours or so. It can harvest that interference and then use it for its sensing and communication and compute tasks. So that's one example. There are other examples also. I wouldn't say harvesting, but you can talk about cancellation. So even though there is interference, if it's very strong, it's actually advantageous because then you can decode the interference and just cancel it out. So one of the technologies that I mentioned was NOMA, non-orthogonal multiplexes. That's in fact what happens at the receiver. One of the receivers actually actively seeks out the other user's interference, cancels it out, and then essentially works in an interference-free world. So it is possible. There are many ways to deal with interference. Yes.
Okay, thank you. One more question by Anonymous. On quadratic feedback, this seems pessimistic. Is the connectivity and hearability that dense? Isn't there sparsity in network connectivity coming from geographic separation?
So a couple of answers to that. There are multiple questions actually that are there in one. The first thing in wireless is geographic separation is really not a measure of how much interference you see. Because when a signal propagates, yes, with distance it does decay, but there's more to it. There's something called shadowing, which is a measure of, if a signal passes through a building or a human being or a chair, that itself causes attenuation. So on top of distance-induced path loss, there's also additional losses or gains called due to shadowing and also due to these multipaths aligning in phase or out of phase. That's called small-scale fading. So in a nutshell, you never have geographical separation as being a measure for whether to pair users or not. It's a good way to think of the problem, but never a good way to implement a solution. That said, yes, there is indeed sparsity. The order m² feedback was yes, just to make you afraid. When you design feedback schemes, for example, we've shown that you measure and you exclude the L strongest interferers. Okay, so you tell the base station, these are the guys, L folks who are harassing me the most. Please don't pair me with them. Anybody else is okay. And using that, you can, for example, really get around this problem. So there are definitely ways around it, and your intuition is right.
Thank you, Nilesh. I think that's all we have as far as questions go. I think it was an excellent and engaging talk, very informative. And, I think the best part of the talk was that there was not even a single equation in the entire talk. I think you perfectly tailored it to the institute audience very well. We have had a very large number of attendees for this talk. And so thank you so much for taking your time off and giving us a very nice talk. Thank you and wish you all the very best for you. And I would like to thank Professor Rangarajan for presiding over this Institute Colloquium talk. And today's talk happens to be the last in the series of 6 Colloquium talks for this year. I would like to thank Mr. Veeranna for organizing this event, and also the public relations of the PRO office for all the online arrangements. So I would like to thank everybody associated with this. I would like to thank all the participants for attending in very large numbers. So Professor Rangarajan, would you like to say anything?
No, nothing much. Yeah, Nilesh, excellent talk. Thank you. So I thank the audience also for attending. That's it.
Thank you very much. I just want to make an announcement that there will be another talk today at 7 p.m. Professor VVS Sharma Memorial Talk. That is going to be given by Professor K.S. Trivedi. The link to that talk is available on the IISc website. So a very cordial invitation to all of you for Professor K.S. Trivedi's talk also. Thank you very much, and wish you all the very best, Nilesh, once again.
Thank you. Yeah, thank you very much.
Yeah. Thank you, sir. We'll close this.
Thank you, Mr. Veeranna, for all the excellent.
Sir, we'll close this.
Yes, sure.
Yes.